Hello everyone and welcome back. Today I'll be talking about the last part of chapter 4, chemical bonding, bond lengths, bond energy and shapes of molecules. You can visit us on the website where you can find the material, and you can also subscribe to our YouTube channel to be updated by our latest videos. So first, what is the bond length and what is the bond energy? If I looked at something like hydrogen, H2, hydrogen gas H2, I have two nuclei with one proton inside and one electron outside. My bond length would be the length between these two nuclei. The distance between these two nuclei will be my bond length, and the energy required to break this bond will be my bond energy. Looking at values of bond energies and bond strengths, we could and bond lengths, we could look at this table and we see that the bond between two carbon atoms is equal to the bond energy to break them is equal to 350, and the bond length 0.15, while C double bond O is much higher, almost twice the amount of I need to break C bond O, and the bond length is shorter. This means if I increase the number of bonds, I'm increasing the bond energy and I'm decreasing the distance between the two nuclei because of the attraction between the two nuclei. If I looked at C bond O, I could see that it's 360. It increased when I moved to C double bond O, which is 740. Because I increase the bond, I will increase the energy I need to break these two bonds. Instead of one bond, I'm breaking two bonds, and my bond length is actually decreasing because these two nuclei will be attracted more to each other. I also have to look at the reactivity, and my reactivity is actually increased by decreasing the bond strength. So in here, if I looked at this bond strength is less than this bond strength, so my C bond C will be more reactive than C double bond C. If I looked here at this C bond O and C double bond O, I could see that C bond O is more reactive than C double bond O. Also, another example between, if I compared between nitrogen and the oxygen, I could see that the nitrogen is bonded with three triple bonds, while oxygen have only two bonds. So nitrogen will be less reactive than the oxygen. By that, we could say that the chemical reactivity is affected by the bond strength. If I have a stronger bond, I will have more stable compound with less reactive compounds, and the polarity of the bond, if my polarity increase, this means my reactivity increase. I could see that in here C double bond C, I have a value of 610, which have the same electronegativity, while C double bond O, there is the difference in the electronegativity, so there is some polarity in that compound. This is why I increased my bond energy. And the type of the bond, if I have sigma bond, it will be harder to break it, while pi bond is easier to be broken. If I looked at this, at the example in here, I have a table lists three halogens, HCl, HBr, HI. If I looked at their bond length, I could see that moving from chlorine, bromine, and iodine, I'm decreasing my bond. I'm increasing my bond length, while my bond energy is actually decreasing. This is because when I move from chlorine, bromine, iodine, I'm increasing my atomic number. So I'm increasing the size of my radii, which will increase my bond length, and by that my bond energy will decrease. If I try to suggest a value for hydrogen fluoride, this means hydrogen fluoride actually lies above the chlorine atom, so the hydrogen fluoride would be around here. And if I try to find the bond length, I could see that moving from this value to that value, I add around 0.041. So for that, my bond length in that case should be here 0.113, which is less than this value with around 0.041. As for the bond energy, I could see I'm decreasing each time I'm moving down around 65 kilojoule per mole. This means the hydrogen fluoride would be around 400 96 kilojoule per mole. Now, if I try to explain the shapes of the molecules according to the electron pair repulsion theory, first, the electron pair repulsion theory states that electrons repel apart electrons until the repulsive forces are minimized. The shape and the bond angles of a covalent bond molecules depend on the number of the pair of electrons around each atoms and whether these two pairs are lone pairs or bonding. The lone pair have more concentrated negative charges. This is why they will repel more comparing to a bonding pairs. So if I try to look at the bond between the repulsion between lone pair and bonding in water molecule, I could see that between the hydrogen and the hydrogen will be the bonded pairs. This will make them the less repulsion between these two atoms, while this is the lone pair and the lone pair, the repulsion between these two lone pairs on the oxygen atom will be the highest, while the repulsion between this lone pair and this bonding will be almost in between the value of the bonding and the two lone pair repulsion. Now, if I try to work out some of the shapes, I could see that first example have methane. If I have this structure only and I try to work out what is the shape here, I could see that I have in methane, I have 4 bonding pairs. So the repulsion between these 4 bonding pairs should be equal. And if I try to divide my angles over 4 pairs, this means the angle between the 4 of them is around 1.9, and by that they will be able to form a tetrahedral structure with a bond angle between each one of them is equal to 109. If I looked at another example, the ammonia is different. That I have in ammonia I have 3 bonding and I have 1 lone pair on the top. This lone pair will have higher repulsion between the other 3 bonding pairs. If I looked here, I could see that my lone pair will stay on the top of the plane, while the 3 bonding will remain on the same plane, and by that they will form a triangular pyramidal shape. This triangle pyramidal shape will have bond angle between H and H. This one will be this one or that one will be around 107. If I looked at another example, the water again here, and I try to look at the shape of this molecule, I could see I have 2 lone pairs. These 2 lone pairs will stay away from my plane, while the 2 bonding pairs will stay in the same plane. So this will make it non-linear V shape between this HOH angle with an angle equal 104.5. So we could see that if I'm increasing the number of lone pairs, I'm increasing the distance between the lone pairs, or the angle between the lone pairs and any bonding around it. In here I have this lone pair separated from this 2. If I looked here at the angles, I could see that I'm decreasing the angles between the bonding pairs because I'm increasing the number of the non-pairs in each one of them. In here, I didn't have any lone pairs, so I have equaled angles. But in here, I have the angles is almost 107 to stay much apart from my lone pair. And in here, even the bonding pairs decreased the angle between them to be able to stay much apart from the 2 lone pairs on each side of the molecule. If I looked at a more complicated molecules, something like phosphorus pentafluoride, I have here 5 fluorine atoms bonded to the same phosphorus atom. This will make 3 of them will stay in the same plane, and 2 of these fluorine atoms will be one on the top plane of the plane and one in the bottom of the plane, forming what we call triangle bipyramid with an angle equal 90, and the 3 that lies in the same plane will have 120 in between. If I looked at the sulfur hexafluoride, I could see that there will be an angle equal 90 between sulfur and each fluorine atoms. This will form a shape that we call it octahedral shape. Now let's talk about sigma bond and pi bond. In general, the covalent bond forms between the non-metals. The occurring of this bond will happen between atomic orbitals with unpaired electrons, and the combination between both of them will result in what we call it molecular orbital. The amount of overlap would determine the strength of the bond. The greater the overlap is, the stronger the bond will be. Now if I looked at something like H2, I have here overlap between 1s and 1s to form this molecular orbital. This covalent bond with a sigma bond between both of them is actually a very strong bond. If I looked here at the p orbital, I could see that p orbital overlapping with s will be called hybridization. If I have s orbital that hybridized with a p orbital, they form either a sigma bond, like in here, because it actually interact head to head in a linear way, forming this molecular orbital with a sigma bond in between. Example to that, the bond between the C and the H. Another example, the overlap of p orbital with another p orbital. The p orbital with another p orbital, they can form sigma bond if they overlap head to head. While there is another possible way in the overlapping between the two p orbitals, which is the sideway. This parallel sideway will form what we call bi-bond. Now, if I looked at carbon hybridization, first case in case of ethane. Ethane, I have between them, I have C bond C and I have C bond H. In C bond H, it is a sigma bond, and C bond C is also a sigma bond. This sigma bond that happens between the C and C is actually due to the hybridization between the S and B orbitals. In that case, I have two mixed orbitals. In carbon, I have 6 electrons. The first one, 1s, will be discarded. In that case, I will just look at the another orbitals, which is the another 4 electrons in the 2s orbital and 2p orbital. In the 2s, in that case, I will have the carbon with the 3 orbitals have 1, 2, and the s is actually 2 electrons. These 2 electrons, one of them will be excited moving up to the p orbital, and by that I will have 1 electron in that orbital and 3 electrons in the p orbital. Then hybridization will happen. This hybridization will happen between 3 p orbitals and 1 s orbitals. So the sum will be around 4 sp orbitals. So this 2s will increase little bit in the energy and this will decrease little bit in the energy, so both of them will be on the same level, forming the sp orbitals. And the hybridization, in that case, I name it sp3, and this 3 refers to how many p orbitals involved in the hybridization. Let's move to the ethane. In the ethane, I have the same thing. I have here, in ethane, I have C double bond. Now let's move to the ethene. Ethene, it have this C double bond C, and I have 4 hydrogen around my carbons. In that case, if I looked here, this means I will have here sigma bonds. In that case, 5 sigma bonds four of them C bond C, C bond H, and the C bond C will have one sigma bond and another bond will be pi bond. How did I know that? If I looked here at the C double bond C, I have here in the first case I will have the four electrons distribution of the four electrons. Two of them will be in the 2s and the 3 will be on the 2p. Then these electrons will be excited, so this electron will be excited moving to that part. Then the hybridization will happen. In that case, the hybridization will happen between 2p orbital and 1 so orbital, forming 3 ps orbitals, and 1p orbital will not be be involved in this hybridization. By that I will have 2p2, and like I said before, the 2 here will indicate how many orbitals involved in the hybridization. In that case I took 2p orbitals. In the first one I took 3, so I wrote here 3. In the ethene I took only 2p orbitals, so I write 2. If I look here at this bond, actually this is what will form the pi bond. So if I have p orbital that is not forming the hybridization with the s, this means it will form the pi bond. If I looked here at the molecular structure of the ethene, I could see that the sigma bond will happen in that case on the same plane of the CHs, the 4 CHs. So I have 1, 2, 3, 4, 5 sigma bonds, and the pi bond will form between the last p orbital BZ. Now if I move to ethine, in ethine I will have the 4 electrons. One of them will be excited from 2s moving to the 2p, and the formation of the hybridization will happen only between these two. So I took only 2p. This is why my hybridization I will name it sp only, because I took only one orbital of the p. I will be left with the by and the bz. The by and the bz, both of them will form double bonds. If I looked here at the molecular structure, the distribution of the bonds, I could see that I have ethene, C bond C, and triple bond CH. So the H's will be at the end of the my structure, forming sigma bond. So I have 1, 2, and between the C and C will have one only sigma bond, because I have here sp orbital forming, and in that case I will have 2 empty p orbital orbitals available to form the pi bond. So I will have the bz forming one of the pi bonds, and the other by forming the last by forming the last pi bond. 3 sigma bonds, and I have 2 pi bonds. Now if I try to look back at the relation between the bond type and the physical properties. Now if I try to put the relation between the bond type and the physical properties. For ionic compounds, most of the time they are solids at room temperature and pressure. This is because of the strong electrostatic force that holds the positive and the negative ions together. Those ions are regularly arranged in a crystal lattice and have a very high melting and boiling point due to the strong bond. They are all soluble in water, forming ionic dipole attraction, replacing the electrostatic forces between the ions. So the ions will be something like NaCl. The bond between the positive ion and the negative ion will be separated, forming instead ion dipole attraction with the water molecules. They don't conduct electricity in their solid states because ions are fixed, but if I molten ionic compounds, they will be able to conduct electricity because the ions in that case will be more mobile. Now if I looked at the metallic bond, it happens between metals. It happens actually between the positive ions that is in a sea of delocalized electrons, and the attraction will be between the positive ions and the surrounding electrons of the other atoms. It is a very strong. It happens between metals, and we all know that metals have high melting point and high boiling points. Also, we know that it is a very strong metallic bond, prevents them from dissolving in water, except for alkali metals or alkaline earth metals, because they have only few electrons. Example for that, if I have something like sodium, I have only one electron that is free to move, is forming the delocalized electrons for each atom. So one electron makes the sodium bond, the metallic bond, is very weak. This is what makes sodium metal dissolve in water. If I looked at calcium, I have only 2 electrons. These 2 electrons also will make the calcium metallic bond weak, and it make it enable it to be solubilized in water. Also, metallic bond to conduct electricity. Now, if I looked at the covalent bond, they have simple molecular structure, and the forces between molecules are weak. They have low melting points, and they have very low boiling points as well. The covalent bonds covalent bond substances do not have ions nor electrons to conduct electricity. I have 3 types of covalent bonded substances. Some of them that dissolve in water, and some of them doesn't dissolve in water, and some of them, instead of dissolving, they will react with water. The first type, the covalent bonded substances that dissolve in water, they have small molecules that enable them to form a hydrogen bond with water. Example to that, the ethanol. As for the covalent bonded substances that doesn't dissolve in water, are non-polar substances that will not be able to dissolve in water due to the fact that water molecules will not attract them. Example to that, the iodine. As for the covalent bonded substances that react with water rather than dissolving in water, example to that, hydrogen chloride. The third type is a covalent bonded substances that will react with water rather than dissolving in water. In that case, what will happen? What we call it hydrolysis. Example to that, if I have hydrogen chloride, when it is placed in water, it actually react with water. By that, we came to the end of our video and the end of chapter 4. My next video will be about chapter 5, states of matter. Till next video, thank you and goodbye.